Hi, my name is Nick Wu, and I'd like to talk about unifying structured recursion schemes, which is joint work I did with Ralf Hinze and Jeremy Gibbons that was presented at ICFP 2013. So I'd like to start by taking you to the wonderful zoo of morphisms, where we'll meet a whole range of different animals that we've collected over the years from the wilderness of functional programming. First, of course, is the catamorphism, more commonly known as a fold, and is, as we shall see, in many ways the king of the jungle. He loves to chase the results of the anamorphism, which unfolds values from a given seed. Now, another variation of the anamorphism is the apomorphism that likes to monkey around and stop a computation whenever he likes. Let's not forget the paramorphism that repeats the values it has given and provides them as parameters to recursive calls. Now, one of my favourites is the mutuomorphism that captures mutual recursion, and its close cousin the zygomorphism, where only one function depends on the other. Then we have a number of more exotic animals that aren't so well known, such as the histomorphism for coarser value recursion, and the dynamorphism that captures dynamic programming. Oh, and as a jewel of the histo, there's the futuomorphism, and in case you thought I'd forgotten, we can also compose various morphisms and end up with things like the amazing zygohistomorphic prepomorphism. Well, this is all getting a little bit silly, so let's focus on something we know and love, the catamorphism. Now, a catamorphism, or more commonly known as a simple fold, works on the fixed point of a base functor d. A simple example of one of these functors is natf, which is made up of either 0 or suc(x), where x marks the spot of recursion. The fixed point of this is simply the natural numbers. A fold takes an algebra, there on the right-hand side of the diagram, from dA to A as its input, and produces a morphism x from the fixed point mu d to A. In other words, it crushes the structure of d into some value. This is achieved by using the isomorphism called in, which has as an inverse what we call inwoc. Inwoc takes a fixed point of d and exposes one layer of d's recursive structure. So, starting on the bottom left of the diagram, at mu d, we can apply inwoc to give us d mu d, then recursively apply x to turn the recursive structure into dA, and finally use the algebra A to turn this into a final result of type A. We tend to use special notation for x since it is uniquely defined. It is the fold of A from mu d to A. Now, as we saw in the introduction, the catamorphism is just one of many different recursion schemes. But why are they so useful? Well, they tend to have nice calculational properties. You might have heard of fold fusion, which is a way of optimizing recursive functions. They also make reasoning about the termination or productivity of a function explicit. Oh, and they're pretty easy to work with, since you need only focus on one step in a recursion to produce a definition. But with so very many different variations, an obvious question is whether or not we can unify them. In fact, there have been a number of attempts. In 2001, Uustalu, Vene and Pardo presented recursion schemes from comonads, which I'll call RSFCs for short. You'll note that there are some similarities to catamorphisms on the left of the diagram, but on the top you'll find that there's this n structure. Here n is a comonad. You can think of this n as a store, although I find it helpful to remember it as being an n environment that holds computations, which acts a bit like a call stack. The rough idea is to use the function fan to embed a subterm into the store for later retrieval. So, along the top of this diagram, we are creating an environment that makes the results of recursive calls available to the structure DNA on the top right. This additional information gives the algebra A more to work with, and is key to the generality that this scheme provides. In fact, the authors showed how to generalize almost every scheme I gave in the introduction, but it doesn't work for generalized folds or nested data types. Now, a different approach to unification was given by Hinze in 2012, where he introduced adjoint folds. Here, the right-hand side of the diagram is similar to that of ordinary folds, except that the structure D has been replaced with a C for control structure. This scheme changes the structure of the input mu d by wrapping an additional functor L that provides more control over the shape of the input. Now, the data structure and control structure are related by sigma, which is a natural transformation that acts as a kind of impedance matcher between the two. When it was introduced, this scheme was shown to cover generalized folds and nested data types, but it wasn't clear how histomorphisms fit the bill. So a natural question to ask is whether or not these two general recursion schemes can be combined in some kind of grand unification. Putting these two diagrams side by side, we can see that they're rather different, and indeed Hinze said that we cannot reasonably expect that adjoint folds subsume all existing species of morphisms, and in particular, he says, for instance, a largely orthogonal extension of standard folds are recursion schemes from comonads. So, for a while it seemed rather unlikely that some unification exists, but it turns out that it does exist, and that's what this paper is about. Let's start with a simple example to understand the technique we use to show this unification. The humble mutuomorphism is a good place to start. Mutuomorphisms capture mutual recursion, which is easy to see in the functions even and odd, where even depends on odd and odd depends on even. We can think of these as two separate functions that return two different results. They're on the left-hand side. But you can also think of them as a single function that returns a pair of results, one for each of the constituent parts. They're on the right. If we look at what's happening from a categorical perspective, the pair of functions on the left is really the mutuomorphism. So let's focus on the left-hand diagram. Here we're working in the product category, and on the bottom left we have the triangle symbol delta, which duplicates its argument mu_d. We're working with a pair of functions from a common structure and embedding them into A, which is a pair of values since this is the product category. The point here is that we have two mutually recursive functions. What we saw on the previous slide is that this is equivalent to the diagram on the right-hand side, where we're going from a single value mu_d to a pair of values A with just one function. It turns out that this function is related to x in a pretty special way, so the question here is whether or not this can be generalized. Well, let me take you back further into history to 1958, where Kahn introduced the notion of an adjunction. An adjunction is a relationship between two categories, given by a pair of functors L and R. Perhaps the simplest definition is this equation, which simply says that the morphisms or arrows in C, from LA to B, are isomorphic to the morphisms in D from A to RB. In essence, we can transform a function with the structure given by L on its input into a function with structure given by R in its output. MacLean famously said that adjoint functors arise everywhere, and we'll see that this applies equally to our recursion schemes. To get a better grasp of adjunctions, it might help to think of currying. There, the isomorphism is given by a function we call curry, that takes a function whose input is a pair of values, and what it produces is a function whose output is another function. We have modified the structure of the input into a structure on the output. Of course, this goes both ways, and the inverse is given by uncurry, so this forms an isomorphism. We tend to call functions like curry and uncurry the adjuncts of the adjunction, where curry is the left adjunct and uncurry is the right adjunct. Now for our mutuomorphisms, the isomorphism is between the product category C cross C and the underlying category C. The left adjunct takes a function with input A, whose structure has been duplicated by delta, into a function whose output is B, which is a pair in the underlying category. So back to mutuomorphisms. It should be clear that mutuomorphisms are related to folds by an adjunction. In particular, the morphism on the bottom right-hand diagram is in fact the result of applying the left adjunct to x. We tend to call this the transpose of x. So this is clearly an adjoint fold. More generally, the story reveals that the adjoint folds are related to ordinary folds. The technicality that I'm brushing to one side here is that the sigma on the top of the left-hand side diagram essentially turns into a tau on the right-hand side of the diagram. You can read the paper for more details. So how does this construction relate to RSFCs? Well, to answer that question, we need another lesson in history. In 1961, Huber showed that every adjunction gives rise to both a monad and a comonad. If L and R are left and right adjoint, then starting in the category C on the left, the composition of doing R and then L is a comonad, and starting on the right in the category D, the composition of doing L and then R is a monad. Now, a very interesting question is whether or not every monad or comonad gives rise to an adjunction. Well, it only took a little while for that question to be answered. In fact, it was answered in two very different ways, once by Kleisli and again in 1965 by Eilenberg and Moore. we'll focus on the Eilenberg-Moore construction. Well, technically the co-Eilenberg-Moore construction, which basically says that for any comonad n, we can derive functors un and cofree n that are adjoints. So back to our problem. How are adjoints related to recursion schemes from comonads? Well, let's take another look at the RSFC. Putting this to the left-hand side, we want to show that this is equivalent to a fold. Now, I'll leave the technical details to the paper, but essentially we can show that RSFCs are equivalent to folds of this form, where A sharp is related to A. And if we move things around a little bit and think hard, we might just notice that this is actually just an application of the co-Eilenberg-Moore adjunction. In particular, nx after fan is the transpose of x. Okay, so maybe you really do need to read the paper to understand this part, but hopefully you understand the main idea. So let's go back to the zoo. It turns out that all of the different recursion schemes that we know of are related by some adjunction. And here's a table that shows some of the main results. In summary, it turns out that adjoint folds are general indeed. The main result is that every RSFC is in fact an adjoint fold. The details are a bit technical, but it turns out that under special circumstances, namely when sigma is isomorphic, that adjoint folds are also instances of RSFCs. But in general, adjoint folds are strictly more powerful. So I'd like to end with another historical note that summarizes what we've done. There are known knowns. There are things that we know that we know. There are known unknowns. That is to say, there are things that we now know we don't know, but there are also unknown unknowns. There are things that we do not know we don't know. And I'd like to add that, finally, there are unknown knowns. That is to say, there are things that we now don't know we knew, but we know they make good research papers. Thanks for listening.